Check this out. We've got something really fun today. This is so amazing. Oh man, again?
11.6 Partial fractions. We've added fractions like this before, so as a review, let's add these together. They need a common denominator, so we'll multiply this one by x plus 2 in the numerator and the denominator. When we're writing it in the denominator, don't write it like this, because then it looks like you're only multiplying the x by this binomial, and we don't want to do that. We want to multiply the whole denominator. This side here we'll multiply by x minus 1, numerator, and denominator. So in the numerator here, we have 2 times x plus 2 and 3 times x minus 1. In the denominator, we have these two binomials, x plus 2, x minus 1. And really, we don't care about multiplying these together. You can if there's a reason to do that. Otherwise, it's fine leaving them like this. But let's multiply these in and collect up the like terms to simplify the numerator. So again, let's just leave the denominator factored here, and in the numerator we get 5x minus 1, and we've added them together. What if we want to reverse this process? Take this fraction and back up and break it into two smaller fractions. The technique we're going to look at here is called the method of partial fractions, breaking a fraction into simpler fractions. The first example we will look at is undoing what we did on the previous slide. And you can note that this denominator has two distinct linear factors. We know how this one's going to look. There's going to be some term over one of the factors, and then another term over the other factor. We're going to take this whole equation and we're going to get rid of the denominator by multiplying by x minus 1 and x plus 2. So we'll just write that here. We're multiplying the entire equation by these two factors. That will get rid of the denominator completely. So on the left side here, we'll just be left with the 5x plus 1. And on the right side, when we distribute in these two binomial factors, the x minus 1 will cancel here, and we will just be left with the x plus 2 with the a. When we multiply them into this term with the b, the x plus 2 will cancel, and we'll just be left with the x minus 1. Now we'll distribute in the a and b and collect up the like terms. And we get ax plus bx and 2a minus b. I'm going to factor out the x's, and you'll see in a second why we would do that. And I'm just going to put these two in brackets so I can see that they are together. Now you can see that 5 is equal to a plus b, because 5 is the coefficient of x on this side, and a plus b is the coefficient of x on this side. 1 is the constant term on this side, and 2a minus b represent the constant term on that side. Now you can see that we've ended up with just a linear system to solve, and it's set up nicely for elimination. So I'll add these two and get 6 on the left and 3a on the right. So we can see that a equals 2, and then using the first equation, b equals 3. And now we can write out the partial fractions for 5x plus 1 over x minus 1, x plus 2, and it equals 2 over x minus 1 plus 3 over x plus 2. And you can see that this is exactly what we started off with on the previous slide. Why would we want to use partial fractions? Well, the partial fractions are going to be simpler than the original. And when we're trying to integrate a rational, it would probably help us a lot. Let's try this one. The next case is where the denominator has some repeated linear factors. So I'm going to find its partial fractions first, and then I'll integrate. So 6x plus 7 over x plus 2 squared is equal to some constant over x plus 2. And in the next one, I'm going to do the other factor of this, which is x plus 2 squared. Now you might think that's a bit funny, but this will guarantee that we find a partial fraction. Okay, so same drill as last time. We're going to multiply the entire equation by x plus 2 squared to get rid of it. And on the left, we'll just be left with the 6x plus 7. This a will be left with one of these. So just one x plus 2, the other one gets cancelled out here, and the b actually is single and available. So both of these get cancelled out. Same thing as before, distribute in the a, collect up the like terms. We got ax and 2a and a 2b. There's just one x term, so that means that a is equal to 6. And the other one is 7 is equal to, these will be the constant terms here, so 2a plus b. Now we know that a is 6, so that actually means that 7, 12 plus b. So b must be negative 5. Now I can break this up before I integrate. So I've got first a, 6 over x plus 2, and minus a 5 over x plus 2 squared. And these are a lot easier, you can see. This one will just equal 6 natural log of x plus 2. And this one, you can think of x plus 2. There's a 5 here, and that used to be x plus 2 to the power of negative 1. And the negative 1 will come down, and we need a plus here, so we end up with a negative. And the inside, using the chain rule, the derivative of the inside is just 1, so we don't need to worry about that. And we can use a plus c. And if you don't like negative exponents, then how about this instead? This pattern would continue if we had more factors in the denominator. So we see that x repeats, it's x squared, so we need a term with just an x and then an x squared. This x plus 2 is to the power of 3, so we need an x plus 2, an x plus 2 to the power of 2, and an x plus 2 to the power of 3. Now, we won't be doing questions like this. Just because it's a linear system with 5 unknowns, it will take a long time. You should have all the skills that you need to do it, though. And any one of these could be 0, and that would mean that we just didn't need that term, and that's fine. But we're just looking for all the options by doing this pattern. And now we have non-repeated, irreducible quadratic factors. That would be this one right here. It's a quadratic one. We can't factor it, so that's what we were calling irreducible. And it's not repeated. There's just one of them here. Now let's find the partial fractions for this, because we definitely can't do the antiderivative in this state. So we will say negative x squared plus 3 over x minus 1 squared. This one is repeated, but it's just a linear factor. X squared plus 1. And we know what to do with this. It is a over x minus 1 and b over x minus 1 squared. For this quadratic one, though, we've got to put a linear function in the numerator. So we say cx plus d over the x squared plus 1. And now we do just like we did before. Multiply by this common denominator to get rid of it all, and then collect up the like terms, solve for a, b, c, and d. So I won't show the multiplying this time because you know what I'm doing by this point. So for a here, a is going to be multiplied by x minus 1, and also this one here. B is going to be multiplied by this one, and the cx and plus d is going to be multiplied by the x minus 1 squared. Now this is going to get an awful lot of terms to it. So first I'll multiply these out and then multiply in the a. So this would be x cubed plus x minus x squared minus 1. And this one's already good. And this one, I'll square this term here, cx plus d times x squared minus 2x plus 1. Now I'll distribute in the ABCD. So that ax cubed plus ax minus ax squared minus a plus bx squared plus b plus cx cubed minus 2 cx squared plus cx plus dx squared minus 2 dx plus d. Oh, it didn't make it. Now we'll collect up all the like terms on the right side here. And that would be a x cubed and a cx cubed. Next we'll look for all the x squared. So we've got a negative ax squared and a b x squared and a minus 2c x squared and a d x squared. Next we'll look for all the x terms. So that would be a and c and minus 2d. And now just the constant terms. So there's a minus a. I'm going to put a plus and then use brackets. Minus a plus b plus d. Okay, now let's make the equations from the left here. So we know we have 0 x cubed. So the coefficient of this x cubed has to equal 0. So that's my first equation. 0 equals a plus c, because I don't see any x cubes over here. This, all of this, is the coefficient of x squared, and that would be negative 1. Next, the x's, and we don't have any of them either, so that coefficient will be 0 as well. And last, our constant here is 3, and that will equal negative a plus b plus d. And now we have to solve this linear system. So it looks like the first and the third equations are very similar here. And if we subtract them, we'll say 1 and 3. Subtract, and we get 0 and 0 and 0 and 0, and this would be 2d. So 0 equals 2d means that d is equal to 0. So that's the first thing that we find out, which is actually kind of helpful. If d is equal to 0, then we don't need to worry about this or that. Let's see what else we can do then. We've got this number 2 equation and this number 4 equation. Let's put them together, yeah, because the a's and the b's match up. So the number 2 and the number 4 equation, just numbering them so you can see which ones I'm using. So -1 equals -a plus b minus 2c. Not worrying about d because it's 0. 3 equals -a plus b. Okay, and they're the same, so we will subtract this equation. So -1 minus 3 is -4. And the a's and the b's cancel, and just left with a -2c. And that means that c is equal to 2. Now let's go back. Here's a nice one to solve for a. So if c is 2, then a just needs to equal -2. And which one don't we have? A, b. So we use this one to find b. So 3 is equal to -a plus b. So that'd be 2. So it looks like b is equal to 1. Now we can put all of this together and write our partial fractions. So our integral was -x² plus 3 over x minus 1 squared x² plus 1. And we can break it up now into, let's see, first it was a, -2 over x minus 1. And the order matters. So if you forget, just look up there how we had these written. Next we had b is 1. So there was one of these. X minus 1 squared. And last was the c and d term. So this one was 2x. Yeah, the c went with the x and the d was the constant. So d is 0. So it's just 2x over the x² plus 1. And now we can integrate these just individually. So for the first one, we've got -2, the natural log of x minus 1, and then minus, and just keep this one in the denominator. We've got x minus 1, and nothing is coming out of this factor itself, so we're all good here. And this one, you can use substitution if you find this difficult, but I see that the derivative of the bottom here gives us the numerator, so that's a good clue where that came from. I don't need to worry about that. So this one would just be plus the natural log of x² plus 1. And it's an indefinite integral, so I need a plus c. Now this pattern continues if we had repeated irreducible quadratic factors. So the first one's just a linear factor, so when we break it up, then it just has a constant in the numerator. This is an irreducible quadratic factor, and it's raised to the power of 3, so we need to try it to the power of 1, to the power of 2, and to the power of 3. And since it's a quadratic, then we put a linear in the numerator. And we could solve this. It would just take a long time. It would be a linear system with 7 unknowns. All the previous examples that we have done were proper rational functions. That's where the degree of the numerator is less than the degree of the denominator. If the degrees of the numerator and denominator are the same, or if the degree of the numerator is larger, then we want to start with polynomial division and see what we can simplify with that as our first step. So in this example, we see that the degrees are the same, so we're going to start with polynomial division, x plus 4 divided by x minus 2. Goes into it once, and x minus x is 0, and 4 minus -2 is 6. So we can rewrite this definite integral as 1 plus 6 over x minus 2. Now we can find the antiderivatives. This would be x, and this would be 6 times the natural log of x minus 2. We need to evaluate this from 3 to 4. So first we put in 4, and then we'll put in 3, and we're going to subtract that. So minus 3 minus 6, natural log of 3 minus 2. Now 3 minus 2 is 1, so the natural log of 1 is 0. So we're not going to have to worry about this last term, it just equals 0. So we just have 4 minus 3, and then this term here, 6 times the natural log of 2. In this example, we can see that the numerator has a higher degree than the denominator, so we'll want to start off with polynomial division and see where that gets us. So we've got 5x cubed minus x squared divided by x squared minus 1. Our first term here would be 5x. 5x times x squared would be 5x cubed. And then we have a minus 5x. Doesn't quite line up with this, so I'm going to put it over here. And we're subtracting this, so we have 5x cubed minus 5x cubed is 0. We've got a negative x squared plus 5x. And looks like then we'll need a negative 1 next. Multiply that, negative x squared and plus 1. And then we're going to subtract that, so that cancels. Then we're left with a 5x minus 1. Okay, now we can rewrite our integral here. So we got 5x minus 1. And then, quite amazingly, we've got a remainder of 5x minus 1 over x squared minus 1. Now, when I'm looking at this, I take the derivative of x squared minus 1, and I don't get the numerator. So this wouldn't be a good candidate for substitution. Let's try breaking this down using our partial fractions. So we have 5x minus 1 divided by x squared minus 1, and we can factor that into x plus 1, x minus 1. And we see that these aren't repeated, and they're only linear, so we break it up like this, a over x plus 1 plus b over x minus 1. We multiply this whole equation by the common denominator to get rid of it, so we get 5x minus 1 is equal to a x minus 1 plus b x plus 1. Next, distribute in the a and b and collect up the like terms. So we get a plus b x, and then plus negative a plus b. These give us 5 is our coefficient of x, so that means 5 is equal to a plus b. And this second equation is the constant is negative 1, and that should equal negative a plus b. And this is lined up nicely for elimination. So the b's are both here, or addition, can cancel that out. So I guess addition would be the easiest. So 5 plus negative 1 is 4, a plus negative a is gone, and b plus b is 2b. That means that b equals 2. Now if b equals 2, you can easily see from this equation, say, that a is equal to 3. And that gives me my partial fractions. So b was 2 and a was 3. So from here, okay, my b was 2 and a was 3. And now I can take the antiderivative of both of these terms, not a problem. So I can finish up my integral here. The antiderivative of 5x is 5x squared over 2. Antiderivative of -1 is negative x. Antiderivative of this, 3 times the natural log of x plus 1 plus 2 natural log of x minus 1. And we've got to squeeze in our plus c here. You should be able to find partial fractions and use partial fractions to simplify an integrand. Here's some questions from the textbook. Give them a try. See if you know what you're doing.